I'm Anne-Clémence VION, and I'm a researcher in vascular biology working at the Institut du Thorax. And today I will showing you my haut tableau about mechanical forces in intracranial aneurysm. So first, what is intracranial aneurysm? It's a local dilation of the vascular wall that occur preferentially at a bifurcation of cerebral arteries, at the polygon of Willis, at the circle of Willis, at the brain, at the base of the brain. And this pathology usually developed upon hypertension or with aging. There is other risk factors, such as being a woman, unfortunately. Also, smoking and alcohol increase the probability of having intracranial aneurysm. And there is also a second form, the familial form of intracranial aneurysm, that is usually associated with specific mutations. What is dangerous is not so much the intracranial aneurysm per se, but rather its rupture that lead to intracranial hemorrhage that is fatal in 50% of cases. And when it's not, it's usually leading to neurological damage. What is also really bad is that currently this rupture is really unpredictable, and there is no diagnostic tool to know if one aneurysm will rupture or not. And there is also no non-invasive preventive treatment. And one other factor that really contributes to the formation of these aneurysms that I didn't mention yet is the focus of my project is the hemodynamic changes. So basically in the vasculature you have two forces, the pressure that generate a stretch of the vascular wall and that is mostly sent by smooth muscle cells, and the flow that generates shear stress on endothelial cells. And these forces are usually benefic for the vascular wall, but actually, as you can see here, under physiological conditions, smooth muscle cells react to this stretch by becoming perpendicular to the stretching directions, and the endothelial cells tend to orientate parallel to the flow directions. And this reaction is possible because these cells have a lot of mechanosensor molecules at the surface and within the cells. And these mechanosensor mostly converge toward cytoskeleton rearrangement with stress fiber formations or cortical actin formations, depending on the signal. And this cytoskeletal rearrangement is under the control of small g proteins, the raw proteins that are going from an inactive form associated with GDP to an active form associated with GTP, thanks to the guanine exchange factor, a big family of proteins, the GEFs. And now if we come back a bit on our intracranial aneurysm locations, what we can see is that where the aneurysm is forming, the angle of the bifurcation are unusually open. And these generate an increase in stretch and an increase in shear stress locally. And now the hypothesis in the scientific community is that this change in mechanical forces, this increase in mechanical forces, lead to maladaptations of vascular cells that are at the origin of intracranial aneurysm formations. And I want to improve knowledge in that, identifying the key mechanisms at play within the cells. And for that, I'm focusing on this family of proteins, the GEFs. So I'm using in vitro device, one to stretch the cells at the physiological or pathological level, and one to perfuse the cells with liquids to generate shear stress also at the physiological or pathological level. And then, using these cells stimulated with these mechanical forces, I will compare the expression and the activity of these GEFs between physiological and pathological conditions to identify the ones that are mechanosensitive in our pathological context. And now the project is here. So we already have identified 3 GEFs that are mechanosensitive in smooth muscle cells or in endothelial cells. And now we want to know their function, their role. And we focus mostly on the functions regulated by mechanical forces in the vascular wall, such as recruitment of inflammatory cells, increase or control of the permeability of the vascular wall, but also the control of the proliferation and apoptosis of these vascular cells, as well as the control of the vasodilation or vasoconstriction of the vasculature. Once we will know exactly what these gaps are doing within our cerebral vasculature, we hope to be able to design tools to prevent or to stabilize the formation of intracranial aneurysm, but also to design new diagnostic tools that will help the clinicians to know if one aneurysm is at risk of rupture or not, and therefore improve the management of patients. Thank you.